Hello everyone, today we are going to talk about cryogen mass flow rate and inlet-outlet temperature. In this video, we will cover three key topics to explain this lecture's concept. Firstly, we will start with an explanation of what mass flow rate. Secondly, we will discuss the inlet and outlet temperatures. Lastly, we will use a simple example to show how the concepts we've discussed, such as mass flow rate, are applied in simple thermal hydraulic calculations. In the world of classical thermodynamics, a system typically interacts with its surroundings through three fundamental components: mass, heat, and work. In here, the mass flow rate refers to the amount of mass passing through a given system per unit of time. The unit grams per second is often used. Let's consider the cooling system of a superconductor and understand the means of inlet and outlet temperatures in this process. In superconducting systems, additional heat is generated during operation, which must be efficiently removed to maintain superconductivity. This is where the cooling system comes into play. In the diagram on the right, if the cold coolant passes around the magnet or cold head of cryocooler, it picks up heat, resulting in an increase in coolant temperature. After it circulates through the system and absorbs heat from the superconductor, it exits at a higher temperature, which we refer to as the inlet temperature and outlet temperature. Considering the inlet and outlet temperatures is essential for the precise calculation of cryocooler systems. In this page, we will explore the thermal management of superconducting cables using a simple example. The top image displays two samples of superconducting cables. Notably, each cable features a relatively large hole in the center. As shown in the lower image of the cable, this central void serves as a passage for coolant, specifically liquid helium, to flow through and cool the superconducting strands. The design of these superconducting cables allows for the manipulation of the coolant's mass flow rate. By adjusting this rate, we can directly influence the cooling power, specifically increasing the heat transfer coefficient of the system. The graph on the right illustrates the relationship between helium's mass flow rate and the resulting heat transfer coefficient. This relationship was deduced through both experimental data and calculation. On the x-axis, we have the mass flow rate of the helium, and on the y-axis, the convection heat transfer coefficient. From the graph, you can see this increasing of the cooling power as the mass flow rate increases. This understanding allows engineers to design the cooling process, ensuring that the superconducting cables operate within the required thermal conditions. In conclusion, we have examined the definition of mass flow rate, which is the quantity of mass passing through a system per second. We also explored what inlet and outlet temperatures mean within a superconducting cooling system. Furthermore, through a simple example, we saw how the mass flow rate can be utilized to adjust the cooling power. Understanding these concepts is crucial when designing superconducting magnets, as it enables engineers to accurately calculate the heat generated by their magnets and effectively plan the cooling design. This knowledge significantly aids in enhancing the efficiency and reliability of superconducting systems.